Hi there. All right, so today we're going to look at polynomial division. And so far what we've worked with, we've spent quite a bit of time working on those polynomial packets. Remember the whole bouncing and cutting thing? The deal with those, though, is they were already all set up in factored form for us. And so now what we're doing is we're looking at how, if it's not in factored out form, and it's just this big long polynomial, how do we get it into factored form so that we can do the whole graphing and the bouncing and cutting? So sort of that's our goal here for the next few days, is doing division with polynomials to get it into that factored form. Now, I did want to do a quick recap. We kind of pulled away from the book for a few days there, so I wanted to recap just a few things that I maybe didn't officially say, but we kind of figured out. So one of them is called the leading coefficient test. And really, that's just telling us what our end behavior is going to look like. So there's a couple things that we're going to look for here. When you look at the leading coefficient, in this case, the 3 here is the leading coefficient. But we also kind of have to look at the full term because it's an x to the cube, or x to the third. So we know that an x to the third does this kind of a thing. So as far as end behavior, we know that as x approaches infinity, so you're heading up towards infinity, or x is, your y also is approaching infinity. But as you move to the left and x is going to negative infinity, your y is going to negative infinity. And then the leading coefficient test is, well, what happens when that 3 maybe is negative? Well, we know that that flips the graph, and so now your graph is going to do something like this, and so that's going to change your end behavior as x approaches infinity. So the farther to the right we go, the y value is going down to negative infinity, and the farther to the left we go, the y value is going to positive infinity. So that's what they mean by the leading coefficient test, is trying to figure out what the end behavior is going to look like. Okay, the other thing that we haven't really dealt with, and that's because everything was already factored for us, so it wasn't that big of a deal, but one of the things that's kind of cool is what we call the intermediate value theorem. And it indicates where the zeros will fall when they don't end up being nice, pretty integers like they always were with our bounce cut packet. Everything was always a nice integer. Well, what if it doesn't hit at a nice spot on your number line? All right, so we're not going to graph this, but we do need our graphing calculator to look at a table of values. So we haven't done a whole lot with tables, so I'm going to kind of walk us through this. It's a little tricky to do on a video because you can't see your screen, but ultimately what we're going to do is we're going to type this equation into y equals, and we're going to look at what that looks like. Actually, I take that back. We're not even going to look at the graph. We don't want to look at the graph. We just want to look at the table on it. So if you could go in to your calculator, you may end up needing to pause several times on this. I don't want to go super slow, but you need to sometimes pause the video so you can catch up and get to where I am. So I'm putting 3x cubed into my calculator, and I am not going to graph it. Oh, plus 16x squared, doing the whole thing here. And I don't even care about the window. All I'm going to do is I'm going to look at a table on it. So just put it into y equals, and then we're going to go to table setup. Table setup is second window. And when you're going to do a table of values for this polynomial, you have to kind of think, well, where do you want your table of values to start? And I'm going to go ahead and just start it at negative 10. So it's like you're making a table here, and these are your x's and these are your y's, and you're going to start at negative 10. And then the next number is delta table, which means the change. It's the increment. What do you want to go up by? I'm just going to go up by 1s. That's typically the standard. So then my table is ultimately going to look like this. And then it's going to have all the y values. So once you set up your table, you go to second graph, which is the table, and you have it set up. And so I'm looking for, now here's the thing, when I'm looking at this table, what is this helping me for? Well, if I happen to see a 0 over here, if something ended up being a 0 for the y value, that would be awesome. That would be one of the zeros. But so I would know, oh, it's going to cross at negative 8. The thing is, though, that I purposely picked something that doesn't have nice zeros. So it's not really that scenario. What I'm looking for is about where would it fall. So what you do is you track the y values. And if you think of a graph, and let's just do some crazy bounce cut graph here. Something like that. All right. What you have to recognize is every place that you have a y-intercept, right here, and here, and here, and here, you have to look at what's happening to the y value as you switch, as you approach that x-intercept and then cross over it. So when I look at this, I'm coming up here, my y value is down here somewhere, and then I have a 0. And now my y value is positive, 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 positive. Oh, look, I have another 0. Now, it does happen to stay positive because I bounced. All right, not an ideal situation. If I shouldn't have done that. Ignore that. Okay, so now it's going to say positive, 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 positive. Hit a 0. Now your y value is going to end up negative, 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 negative. Oh, now I'm going to hit a 0. So now my y value is positive, 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 positive. And so I'm looking at when that y value switches from being a positive to a negative. So if you look at your table, and I started at negative 10 because I thought that'd give us plenty of room, and you're sitting there scrolling through the y values and looking for when it switches from positive and negative. So when I look at mine, I can see at negative 8, I was just making something up here. At negative 8, I have a negative 167. And then at negative 7, I have a positive 58. Right there, it switched from negative to positive, which means I know that it switched from being below the axis to the above the axis, and the only way that happened is if there was a 0 somewhere between negative 8 and negative 7. All right, so for your notes, let's go ahead and write. We're looking for when the y value switches, I'm just going to say negative / positive. And then I can list every place that I think the zeros will fall. So they're going to fall between negative 8 and negative 7. That's one place. And then I keep scrolling and I'm looking for it to happen again because it could happen more than once. Oh, there it happened. At 0, I have a 9, and at 1, I have a negative 14. It just switched. So I know there's going to be a 0 somewhere between 0 and 1. And actually, it immediately switched back to positive again, so I'm going to have another one between 1 and 2. Now, without looking at your calculator, if you're just like listening, it's going to be harder to tell what I'm talking about. But if you didn't put that in your calculator, weren't following me, you could go back and watch that slide again. Now, I could keep going. Let's keep going. I want to make sure I don't miss anything. I feel like if I get to 10 and you can see the numbers are getting huge, I feel like at that point, I have found them all. All right, that's called the intermediate value theorem. It's where you're looking at a table of values, your zeros don't come out nice, and you're just looking at about where would they fall. All right, let's keep moving. Okay, so now I'm really ready to start 3-3. This is on polynomial division. Now, we have to do a flashback to, I said the 5th grade. I don't know what grade you do long division in, but we have to do a flashback because we're going to do polynomial division. So you need to remember how to do long division with numbers. So let's see how you remember the 5th grade. So we look at 6 is being divided into the 2,845. So you got to look at how many times does 6 go into 28. And 6 is going to go into 28 4 times. So I'd put a 4 above the 8. And then you take the 4 times the 6, and you write 24 underneath here, and then we subtract. So 28 minus 24 is just 4. And then we bring down the next number. And you start all over. So 6 times what would get us 44? Well, 7 is the closest we could do. 6 times 7 is 42. And then you subtract. Is it coming back? Haven't done this in a while, probably. Bring down the 5. And then you do it again. 6 times what gets us 25? Well, the closest I can get is a 4. And 6 times 4 is 24. And then we subtract. And we get 1. And 1 is what we'd call the remainder. And there's a couple things. You might just write remainder 1. Sometimes we would do that. Another thing that you could do, and I don't know that they get into it much in the 5th grade, but you could just say it's 474 and 1/6. You could take this remainder and put it over the divisor. So that's how many times, if you take 6 times 474 and a sixth, you should end up at the 2,845. All right, so now that concept we have to then turn into something with polynomials. All right, I'm going to look at a graph to start this one. Now, we're going to try to get away from the graphs and just try to be able to do these algebraically, but I think it's nice to have a little picture to visualize what's going on here. So in this scenario, you can see that this is a cubic, and it comes up and it looks like it cuts through just barely somewhere right here. It's going to cut up and come back down. And so obviously not very pretty intercepts. But this one looks like a really nice intercept, 2. So what that means is that 2 is a 0. Now, if 2 is a 0 of the graph, then I know that in the equation that x minus 2 would be a factor. So that idea of, usually we go the other way, we do a bunch of factoring, and then we end up with this x minus 2, and we know that means, there's a 0 at 2. So we have to be able to kind of go both ways with that. Typically, we were going factoring to finding the 0. Now I have the 0, I'm going to go write the factor. And because I then know, oops, sorry, I wasn't reading the rest of that. That finished out right here, sorry. Okay, so x minus 2 would be a factor of the polynomial. So that means I'm going to come down here and I'm going to use it to do my polynomial division. Now the equation they had given me was this. It was teeny tiny. You maybe didn't see it, but I went ahead and put it right here. And we're going to take that polynomial and we're going to divide it by one of the factors that I know works in that polynomial because I already know there's a 0 right here. All right, so here we go. Long division with polynomials. Now, I did a very basic 5th grade problem, but if this number out here was like a 2-digit number, we usually would start with kind of the leading number and try to do some mental math with it. So I'm going to kind of just look at just look at the x here and think x times what would get me 6x cubed. And ignore the minus 2 for just this moment, and just figure out x times what gets you 6x cubed. All right, well, that's not too tricky. That's just going to be 6x squared. If I take 6x squared times an x, then I get 6x cubed. Now, just like we did previously, you would then take this times this and write it below. That's what I'm going to do. So I'm going to take the 6x squared times x, and then the 6x squared times the negative 2. And then once we wrote that, we would subtract. So subtracting, I'm going to change that to subtraction, but I'd be subtracting all of it, so it's going to change all the signs. So this minus 12 actually turns into plus 12. All right, so then those are going to cancel, and I have a negative 19 and a positive 12. That's a negative 7x squared. Then we bring down the next number, and we start all over. And we say x times what would get me negative 7x squared. That would be negative 7x. If I take negative 7x times this quantity and then write it down here, so negative 7x times x, and then take your negative 7x times negative 2, and then we subtract. But subtracting kind of just means change your sign, so that would go to positive, that would go to negative. Those will cancel. We want that to happen every time. And then here we end up with a positive 2x. One more time, bring the next number down. And we start over and we say, all right, x times what would get me 2x? That would be a positive 2. Make sure you put your signs up here. If it's just a 2, you have to write a positive 2. If it's negative, then you put the minus sign, because we want that to look like a polynomial. All right, so once you have that, then you're going to take that 2 times this quantity and write it down there. So that's going to be a 2x minus 4. I'm going to subtract, which means change the signs, and look at that. Boom. I got a remainder of 0. Well, I should have, because I already knew it was supposed to work because of this right here. So that's how I know. If I didn't get that 0, I would have been wondering what's going on. Now, our goal, though, remember, the whole reason we're doing the long division is to try to get this messy polynomial right here, this is in general form, and try to get it out in that factored form. And so what ultimately I'm taking this cubic and I'm trying to factor it. The only time we've ever factored cubics is with grouping, and we only did that. We always handed you like this perfect scenario that would factor by grouping. Cubics don't always factor by grouping. Sometimes we have to do this. All right, so here's where I'm at. I currently have an x minus 2. I know that this is going to factor to an x minus 2, and then I have this leftover part. This right here is what's left over after you divide by x minus 2. So that's going to be a 6x squared minus 7x plus 2. But that's a trinomial that I should try to factor. All right, factors of 2, got to be 2 and 1. Signs are the same, both minuses. 3 and 2, probably 2x and 3x. That's a -4 and a -3. There it is. That's it. All right, so what I did is I took this polynomial in general form, and I now have it in factored form, which would then ultimately take me back to being able to graph it, because that's what we did on our bounce cut packet. Look at this. Wouldn't that be an x-intercept of 1/2? And this would be an x-intercept of 2/3, which are these two spots right here that you can hardly tell apart. All right, that's what we've got. So then our final answer is to write the factorization of it, which looks like this. All right, so that's the gist of it. That's what our goal is today, to take general form, put it into factored form. Now, there's some tricky things, so let's look at a few. We'll do a few. It's kind of hard to get the hang of this, but once you have the hang of it, it's just like 5th grade. It just all comes back to you. Okay, so I'm going to write this. What I gave you on this one was a scenario where you are missing some terms. Like I'm just giving you an x cubed minus 1. Okay, that's missing a lot of terms. So anytime you're missing some terms in there, you have to put in a placeholder, because when you do your division, you're going to need that placeholder. So here's how this is going to look. I'm going to take an x cubed plus 0x squared plus 0x, and then the minus 1. And I'm going to divide that by the x minus 1. All right, going to try to go maybe a little faster here. Let's see how we do. So x times something gets me x cubed. That'd be x squared. You take the x squared times the binomial. So that's x cubed minus x squared. See why we needed that placeholder? We need these to be like terms, so they have to line up properly. Change the signs. I have a 0x squared, and this is assumed to be a 1x squared, so that's going to get me a 1x squared. The 1 is totally optional. All right, bring down the next number. X times what gets you x squared? X. And again, that was x times what gets you x squared. So now I take the x times this binomial and write it down below. So that's going to be x squared minus x. Subtract. These cancel. 0x and x is just x. Bring down the next number. X times what gets you x? Well, that's a positive 1. Take the 1 times the binomial. And there we go. Got 0 for a remainder. That's good, because what that tells us is that's truly a factor. And so then I would come back, and I'm going to write it up here for now. I'd have x minus 1 as one of the factors. And then I have the leftover, which is this up here always. And that's going to be x squared plus x plus 1. And then we would try to factor that trinomial. Now here's the thing, though. Last case was perfect scenario. This is not so perfect. Factors of 1 that add up to 1, there aren't any. So this is actually not going to factor. So all I really have is this nice one here. Now, we won't get into why that doesn't factor or what that looks like, but for now, we're just going to leave it. If it's not factorable, then we'll write the x minus 1, and we'll write that resulting quadratic, and just call that the factorization of it. All right, so just kind of a recap, some terminology back from the 5th grade. When you are doing this division, I mentioned this term divisor. The number out here is called the divisor. The part inside is the dividend. I always remembered it was inside. Dividend, in, I don't know. Okay, so the dividend, the divisor, and then the result is always your quotient. What's left down here at the end, we call the remainder. Now, ultimately, what we're going to try to do, that factorization, now, the ones we've had so far came out with a remainder of 0. If the remainder is not 0, here's how we write that. We do the division. I'm probably just going to write an f of x here, because I'm taking these and dividing them. And I'm going to call that the quotient plus the remainder. Remember how I said you could write that over like that 1/6 thing I did earlier? So this plus the remainder over your divisor. This is how we're going to end up writing our result. All right, so let's try a little heftier problem here. This time I'm going to take a quartic, it's to the 4th power, that's my dividend, and I'm going to divide it by this divisor that's a trinomial. So same process, just a little bit lengthier. X squared times what gets you 2x to the 4th? That's a 2x squared. Now you take your 2x, whoa, that didn't mean to do that. Take your 2x squared here and multiply it by the trinomial, and we'll put it here. Oh, I should have looked. I'm the worst at this. Don't be me. You have to make sure that you have a placeholder always. Always make sure there's a placeholder for every term. Otherwise, you find out later that you forgot to sneak that 0x in there or something. So look for that. It happens randomly. So I'm going to take this 2x squared times this trinomial, and I'm going to write it here. And then you subtract, which means go through and change all those signs. So actually, I'm lucky the first terms cancel. The second terms even cancel. That's rare. That doesn't typically happen. And then I have a negative 5x squared and a positive 6x squared. Now, because I have a divisor that's a trinomial, I actually have to make sure I have 3 terms down here. So I'm going to do that. I'm going to have to bring down 2 columns. All right, and then we start over. X squared times what gets us x squared? That's just a 1, positive 1, so put plus 1. Take 1 times the trinomial, so that's pretty easy. But then you're going to subtract it, so change all the signs. So a 3x minus 2x, a negative 2 and a positive 3. And what I have left there then is the remainder. So this one didn't come out nice. It's okay. Not everything does. So what you do then to write your factored polynomial, it's going to be the x, it's going to, okay, sorry, we've already done the division. So you're going to write your quotient, 2x squared plus 1, plus your remainder over your divisor. It looks messy, I know. It's just the way we do it. There it is. That's what the division looks like. All right, so that being said, the long division is really important for us to be able to do because it works well in any scenario. Now, we do have a shortcut, and you probably learned it in Algebra 2, but it only works sometimes, so we still have to be able to do the long division in some scenarios. But I'm sure going to do this synthetic division option if I can. It works if your divisor is in this form right here, where it's linear. That wouldn't have been the case in that previous example, but you just have something like an x minus 3 or x plus 1, something like that, a very simple divisor like that. and you do synthetic division. Now, this is a little diagram from the text. Sometimes I think it's easier just to see an example, but you have this to go back and look at. This is whatever you were subtracting. So notice the opposite sign always. So if the factor is x minus k, you put positive k here. You take all the coefficients of your dividend and you put them across the top. And then ultimately what the synthetic division is doing long division, but just cutting to the chase and just working with the numbers and letting the variables just fall into place. So this is just working on all the coefficients. So you bring the a straight down, whatever that is, and then you immediately take a times that k value, and you write it here. And then you add, and then you take this answer times k and put it there, and then you add, take this answer times k and put it there, add, and whatever you have left at the end is your remainder. Now, because you are taking a polynomial here and you're dividing it by a linear scenario, the power on this is always going to be one less than what you started with. So whatever this coefficient is, it's going to now be an x squared because the original was an x cubed. So this would be something x squared plus something x plus a number, the constant, and then plus your remainder. All right, let's just try one. So the first thing you got to do is figure out what your k value is. In this case, it looks like it's going to be a -3. And then I'm going to look, I've got a quartic going here. Notice that you have a missing term. The x cubed term is not there. So just like in long division, you have to have a placeholder. So I have a coefficient for x to the 4th. I have a 0x cubed. I have a -10. I have a -2, and I have a 4. Don't be too anxious to get these two close together. Spread them out so you don't get them all mixed together and you lose track of those negatives and stuff. Spread them out a little bit. All right, so now you bring the 1 straight down. Take the 1 times the -3 and write it here. And then you always add downward. Then we always take this number times the k. So -3 times -3 is a 9. And then you add down. And then back, take that value times -3. That's a +3. Add down. Take it times the k, -3. So that's a -3. Add down. So what I have left here then is, since the original was a quartic, this is a cubic. So it's a 1x cubed minus 3x squared minus x plus 1 plus this remainder that I would always put over the divisor, the x plus 3. Okay, I guess I wrote it there, but that's ultimately what f of x equals. You sneak in your variables after you have all the coefficients worked through. Works way faster than long division. Okay, this one's for you to try. I know you've done it in Algebra 2. I did one example. Could you set this one up and try it? I'm going to have you pause the video and work through this one on your own. Just doing the synthetic division on it. Okay, ready, stop. Okay, so hopefully you did this on your own. I'm going to go ahead and write it out for us. You put your coefficients. Doesn't look like I'm missing any coefficients this time. And then out here to the side is going to be actually a -2 because it's always the opposite sign. Okay, you come straight down, take it times the -2. Straight down, take it times the -2. Straight down, take it times the -2. Straight down. Okay, this one not as pretty at all. It starts getting to be some big numbers. It's okay. All right, so since the original was a cubic, we know this is going to be a quadratic. So 5x squared minus 18x plus 35. And it's actually going to end up being a minus the remainder over the divisor x plus 2. So really, I'm writing it up there, but I should be writing it down here. I don't know why I'm doing that. Clean it up down here. That's the result of the division. Now, because there was no remainder, because there was a remainder, then I know that negative 2, coming from this factor right here, negative 2 would not have been a 0. So keep that in mind, that when you get the remainder, that's not an ideal situation. What isn't going to play out very nice graphically. All right, so that leads us then to the remainder theorem. And so that last one, that wasn't a good choice because it didn't come out nice. How do you know if it's going to come out nice? Well, you don't always, but we do have a few little tricks to kind of help us. We have something called the remainder theorem. And this is a quick way to determine what the remainder will be if you were to do the division without ever having to really do the division. You can figure out the remainder. So if you look at this scenario, so this is called the remainder theorem. If a polynomial is divided by this divisor, x minus k, then the remainder is always equal to f of k. So if you take this number right here and plug it into the function, it actually tells you what your remainder will be. Let's look at it with the two previous examples we had. So the first one we did there was this x to the 4th polynomial, where I had to put in the 0x cubed on that example. We have this, and we're dividing it by x plus 3. So let's test it with an f of negative 3, because that's the k value. If you do f of negative 3, and so you plug negative 3 into each one of these, let's see what that's going to play out to. So I'd have a negative 3 to the 4th power minus 10 times negative 3 squared minus 2 times negative 3 and plus 4. Now I'm writing that out for your notes. Some of you that are good with your mental math can just do that in your head. That's okay. We're trying to steer clear of too much calculator work, because I'm going to tell you probably on your test you won't get to have a calculator for very much. So negative 3 to the 4th. Can you do that one in your head? I just always think I break it into 3 times. I do a 3 and 3 and another 3 and 3. So negative 3 times negative 3 is 9 times another negative 3, negative 3. That's going to end up a positive 81. Here I'm going to have a 9 times negative 10. Here I'm going to end up with a plus 6 and then a plus 4. And when you look at that, typically, again, if I don't have a calculator to work with, then I kind of group my positives and my negatives. So I have a 6 and a 4. That's 10 with the 81. That's 91 minus 90. That is 1. And if you look back at that example, we did end up with a remainder equal to 1. Okay, let's try it one more time. This one right here, I'm going to let you do this one on your own. Plug negative 2 in for all the x's and let me know what you get. All right, so this was a little harder to do the mental math on. I guess not. This is a positive 10. This is a negative 72. Negative 72 and a positive 10. Oops, sorry. Silly mental math, Goofy. That is actually a plus 2, not a plus 4. All right, so then it's a positive 8 with the negative 72, and that does end up negative 64, which was my remainder on that previous one. So a little messier. Requires a little mental math. You can do it. Just got to practice. I struggled. See, I goofed up. It's okay to goof up sometimes. All right, now here's the thing. The real reason we're doing that is that remainder theorem is my goal is to end up with a 0. Because that's what I want to have happen. I want the remainder to be 0. So that's ultimately the point of the remainder theorem, which leads you to the factor theorem. The factor theorem says that if you can find a k value that results in a remainder of 0, then you've identified one of the factors. So in class, we would have done this. I would have split up the work and we would have separated this all out. I have this function here. Okay, this is my last problem. I know it's gotten long. It's just, It's intense, sorry. All right, so I would have taken this problem right here, and we're going to do some division on it. We're going to try to do some synthetic maybe on it and try to break it down and get its factorization. It's a quartic, so you should end up with 4 factors on it. But where do I even start? Well, I do the factor theorem. I test all these to see which ones come out nice. So again, would have done it in class. I'm just going to tell you the answers. If you plug in -3, you would get a 0. If you plug in -1, you happen to get a 0. If you plugged in 1, you got -40. Plug in 2, ended up with a 0. So what does that mean to us? Well, anytime we ended up with a 0, that means that one would have come out, would have divided, and had a remainder of 0, which means then that those are factors that actually work. The 1 did not get me a remainder of 0, so it is not going to end up being one of my zeros. It's not going to end up creating a factor for me. What this does is it guides me on my synthetic division. So I'm going to do this synthetic division, and I'm actually going to do it multiple times. All right, so here we go. We're going to start with, I have some options that actually work. So let's pick some that actually work. I know that -3 worked. That was the first one I did. So I'm going to put in a -3 here. Put in my coefficients. Doesn't look like I have any missing terms. All right, bring 2 down. 2 times -3. Add down, multiply by the -3. Multiply by the -3. Oops, -6 there when I add down. And then that gets me a +18. Looky there. It's a 0 remainder. I knew it was going to be. I already knew it was supposed to work. All right, now I could rewrite this, but I'm just going to keep moving because I'm now down to a cubic, and that's still not low enough to be able to factor. So now I'm going to come down, do it again with one of the other numbers that I know is going to work. I'm going to try the -1. All right, pull the 2 down. 2 times -1 is -2. Add down. -1 times -1 is 1. Add down. -6 times -1 is a 6, and looky there, that cancels again. So I have done this twice, so my quartic turned into a cubic here, and here it's now a quadratic. So that's going to become 2x squared minus x minus 6. This is the polynomial that's left, and ideally it should then factor. 2x and x, factors of 6, probably going to be a 3 and a 2. Let's go with that and that. -4, +3. There it is. All right, so here are the 4 factors that I have. Originally, I had a -3. That creates a factor of x plus 3. I had a -1 that worked. That creates a factor of x plus 1. And then my resulting trinomial factored to 2x plus 3 and x minus 2. Remember that 2 that worked in our factor theorem? There it is. And this is my resulting factorization, which then would allow me to go be able to graph that a little bit better. All right, so that's big picture. That's going start to finish on that last problem. We will expand on this tomorrow, but hopefully you can get through some of this synthetic division and long division and get the hang of that. All right, good luck. See ya.